To start our discussion here, we're going to have to talk about coordinate axes. In ordinary geometry, we have three axes, x, y, and z. So here's the x, here's the y, and here's the z, all at right angles to one another. These are typically called Cartesian axes from the French philosopher René Descartes. And in general, lines or directions that are at right angles to one another are called orthogonal. So all three of these axes are at right angles to one another, or orthogonal. And the idea of orthogonality is a concept that we're going to generalize later on. But we'll start with it here just as a geometrical idea of things being at right angles. Now, these axes have a particular property in the way that they are oriented with respect to one another. If you imagine, for example, that you point your thumb of your right hand along the x direction, and you point your index finger, or first finger, of your right hand along a y direction, away from you, for example, and then you put your middle finger at right angles approximately to both of these, you have what are called right-handed axes. So this would be the thumb, the index finger, and the middle finger. Now, no matter how you rotate your hand or bend your wrist, the relative orientation of these three axes remains the same. Let me show you what I mean. With my right hand here, my thumb pointing upwards is the x-axis. My index or first finger pointing forwards is the y-axis. My third or middle finger pointing perpendicular to these two at right angles, pointing out from my palm here, is the z-axis. Now, it does not matter how I rotate my right hand. These still remain in the same relative orientation, and they are always right-handed axes. If, on the other hand, you use your left hand with your thumb along x, your index finger pointing away from you along y, and your middle finger at right angles to both of those, with your left hand, you will get what are called left-handed axes. And no rotation of these axes will ever turn them into right-handed axes. You can flex your left wrist as much as you want and move your arm about, but the axes that you get in this way with the thumb, index finger, and middle finger of the left hand are always left-handed axes. We will use right-handed axes all the time, basically, unless for some reason we state the opposite of that. Here now with my left hand, I'll do the same kind of thing as before, but with the thumb on the x-axis, the index finger on the y-axis, and the middle finger on the z-axis of my left hand now. I can rotate these as much as I want, and they still, of course, remain in the same relative orientation. But no matter how I rotate these, they will never turn into those axes. No rotation of left-handed axes will give me right-handed axes. Now, left-handed axes look left-handed to you and to me. Right-handed axes look right-handed to you and to me. If, however, you look in a mirror, left-handed axes turn into right-handed axes, and right-handed axes turn into left-handed axes. Given that we have these coordinate axes, we want to use them to do something, and one of the main things we want to do, of course, is to express the position of some point in space. So we take this point P here, and what we do to express that on the Cartesian right-angled axes is we essentially project the point P onto the various axes. So we can project it over here onto the y-axis, or over here onto the x-axis, or over here onto the z-axis. And the resulting projections, the xp, the yp, and the zp, relative to the origin of this coordinate system, give us these coordinates here for the point P. We can also express those coordinates in terms of these three numbers, xp, yp, and zp, inside these parentheses here. Now, a vector is something with a magnitude, such as a length. This vector here has a length. and a direction. You'll see this vector is drawn as an arrow with a direction that the arrow is pointing in. Usually for vectors, we write them in a bold font. Sometimes when we're writing them by hand, it's not easy to be clear that we're using a bold font, so we can underline them, or we can put this little arrow over the top. And the vector here is shown as an arrow with both a length to it and a direction as given by the arrow. A vector could be, for example, the distance from point A to point B here, and the direction that we have to go between A and B. What direction would we have to walk in, and what distance would we have to walk to get directly from A to B? A vector could also be a force. A force is something with a magnitude of it, how hard you're pushing, and a direction that you're pushing in. So the magnitude in the vector here is the length, and the direction is the direction you're pushing in, the arrow direction here. A vector could also be a velocity. So a velocity is something that has got a magnitude. It's how fast you're going, what speed are you going, what speed is showing on your speedometer. And it also has a direction. What direction are you driving your car in? Are you driving it north? Are you driving it west? Are you driving it east? The direction is given by the arrow, and the magnitude of the speed is given by the length of this arrow. That's a way we could represent velocity as a vector. Now, if we're calling these arrows vectors, what do we call ordinary numbers to get a distinction between the two of them? Ordinary numbers we call scalars. That's a number that has no direction associated with it. So the distance itself is a scalar. How hard you're pushing is a scalar. The speed that you are going at is a scalar. Scalars we write in ordinary fonts without any bold or without any underlines or without any arrows. And usually when we're printing them, we put them in an italic font, which is this slightly sloped font here. Now, a vector has components in different directions. It's one way of expressing a vector. And if we use our Cartesian style of axes here, all at right angles, then we can talk about the components of the vector, gx, gy, and gz, which are the projections of the vector along these three directions. You can see here we're dropping verticals, just as we did when we were talking about a point in space. We can define vectors of unit length along each of the coordinate directions. So, for example, I is a vector of unit length along the x direction. J is a vector of unit length along the y direction. And k is a vector of unit length along the z direction. Then we can write the component of this vector as a vector itself. So the projection of my vector g, which is going to be this line in here, onto the x-axis we can think of as a vector. It has a length gx and it has a direction given by the unit vector I along the x direction. Similarly, the projection of our vector g here onto the z direction is something of length gz and direction given by k, and that could be this green vector here. And finally, the projection of our vector along the y-axis we can show to be gy, this distance here along the axis, times the direction, which is the vector j, the unit vector along the y-axis. So the sum of these three components of the vector gives us the total vector. So we make the final vector up by adding its components together.